Stefan.
No, no, okay, that's fine. Yeah. So it might be a little bit less than 60 minutes. Yeah, but
that's absolutely fine.
Then,
so I think it's probably time to start.
I think so.
Welcome everybody, and welcome to the new season of Global Poisson. So we have a very exciting program during this term. And our first talk is by Stefan Waldmann. The title is KMS Functionals in Poisson Geometry. And Stefan, I give you the floor.
So thank you very much. Yeah, and also thank you for the possibility and invitation to participate here and give this talk. So it's a combination of some very old results and some more recent examples. And so I apologize that already in the beginning, the examples, they are sort of pretty technical, and their status at the moment is not really clear to me, how isolated they are, how general, what one can really expect. It's more biology, what I'm doing. Yeah, it's a zoo, and then I try to catch some of the animals running around. And but I guess it is an interesting question, interesting scenario, what one should take a look at, yeah, and maybe some honest Poisson people should take a look at, yeah, and not me coming here pretty much from outside. So what's it all about? Yeah, so it's about this equation here. This is the KMS condition, and the whole thing emerged from a joint work with Nicolò Drago. He was in Würzburg as a postdoc, and then the pandemic started, and then at some point he went back to Italy and was stuck there. So his postdoc was pretty screwed up, but nevertheless, we've managed to finish this preprint, and so I want to give you some of the results there. So what is all about this KMS condition? Where does it come from? Yeah, so it's originally it comes from statistical quantum physics. Yeah, so and in particular infinite dimensional systems. Yeah, so quantum systems, and it's a condition which characterizes, or which should characterize, thermodynamical equilibrium states. And so if you remember a little bit your textbook quantum mechanics, then you perhaps recall the Gibbs functional, or the canonical ensemble. That's a state on your observables. So the state will be called phi, and that means that the expectation value of a observable A in your observable algebra, this let's say bounded operators on the Hilbert space or something like that. That's a normalization constant, and then it's the trace with e to the minus beta A together with your observable. Yeah. So I have to explain these things. So beta, that's in physics speak, this is the inverse temperature. So K is Boltzmann's constant, and T is the temperature. H is the Hamiltonian of your system under consideration. A is some observable. And the wishful thinking is that e to the minus beta h is a trace class operator, so that this trace, the operator trace, makes sense. And then Z is just a normalization that takes care of this phi to be really a state, so that it's normalized to 1. Yeah? So if you plug in the identity operator, then you get 1. Yeah? So this is the Gibbs ensemble, and the canonical ensemble, and this is believed for many reasons, physical reasons, to describe thermodynamical equilibrium states at temperature indicated by this beta, yeah, for a dynamics for a system encoded in this Hamiltonian H. Now the problem is, if you if you go to more interesting scenarios, this kind of trace class assumption and the assumption to have such a nice Hamiltonian that sort of breaks down. Yeah, this is a strong assumption. I mean, you see that the spectrum of this operator H has to be discrete and growing fast enough so that e to the minus beta is trace class. And in many scenarios, this is simply not the case. And so, to make a long story short, one needs a more general formulation for this equilibrium, which does not rely on having such a trace class operator e to the minus beta h. Yeah? And in particular, this happens to be in quantum field theories. That there it's really serious problem, which one has to take care of. So what is the scenario there? Well, we have usually a time evolution. So that's a one parameter group of automorphisms of your algebra under consideration. So this is really very heuristic. This is not math yet. Yeah. So in particular, the people knowing about operator algebras, they should probably switch off the computer at the moment. Yeah. And then it was then the KMS condition. Is the following, and which replaces this ensemble. So it's a condition with respect to a certain time evolution, which you have for a certain temperature beta, and I'm writing this in quotation marks. So phi satisfies the KMS condition if the following almost trace property holds. Yeah. So you evolve your one observable and multiply it with the other, then the expectation value of these two guys should be equal, yeah, to sort of the order exchanged, but not quite. Here you plug in the temperature, the inverse temperature, and you have to complexify your time evolution. Haha, that's not so easy. And so there's a technical different formulation using using that you need a holomorphic function interpolating between these two values as boundary values. That's the better and more correct one, but heuristically, this is the idea. And if you now plug in, if you go back to the Gibbs function, you can verify this. Yeah. So for the time evolution coming from the Hamiltonian usual Heisenberg equation, then you have this property here with a little bit of analysis to be done in order to justify this holomorphic extension of the time evolution here. But that's where it comes from, and this KMS, I should mention that stands for Kubo, who did this in 57, and then Martin and Schwinger. So that's the KMS in 59. So their formulation was for certain green functions, very complicated boundary condition, blah, blah, blah. You won't recognize it in these papers. Yeah, you definitely won't. And the formulation, the modern or the better formulation, that's due to Rudolf Haag, the famous paper, Gunholz and in 67. Yeah, so they formulated really for states on C-star algebras and made sense out of this condition. And now why is one interested in these kind of things? Yeah. So first of all, if there would be no beta, yeah, then this would be just a condition to banish on commutators. Yeah, that would be a trace. Yeah, and traces, they are interesting. They are interesting. If you have them at all, then they are very interesting functionals. And the more non-commutative your algebra is, the less traces you expect. Yeah, so they become rare and therefore interesting. But you have the beta, yeah. So we will be always interested in positive beta, yeah. So not temperature infinite, yeah. That would be the trace, but finite temperature states, and then this becomes interesting, and so some principal questions are always so given your time evolution and the beta, your temperature. So how many KMS states does one have? And for physical reasons, you would say, well, thermodynamical equilibrium states, there should be not too many, and they should be pretty robust. Yeah? So if you cook everything long enough, then it has fixed temperature and everything looks the same. Yeah? If you boiled it, your system long enough. So you expect to have very few of them, and if you have more than one, then you would say, well, you have different thermodynamical phases. Yeah? You have solids and liquids in coexistence. Yeah? You have phase transitions between different phases if you have more than one such state. Yeah? So this corresponds to phase transitions if more than one. Yeah, that's okay. So this is now just really the physics background here, and now I have to argue a little bit how to put this kind of equation into a Poisson context. Yeah? And so the idea, and that is in fact a very old idea also. Let me see if I find my references here. So taking now a semi-classical limit h bar to 0. Yeah, so taking only sort of the lowest non-trivial orders of this condition here in h bar, and you see there is an h bar showing up, and this is showing up for good reasons. Otherwise, this quantity would not be a time. Yeah, this is for dimensional reasons. There is a h bar, and then you know, well, products are non-commutative. In the classical limit, they become commutative, but the first order correction, that should be the Poisson bracket. And so if you do a little bit this usual yoga of very heuristic semi-classical limit, and then you arrive at the let's say KMS condition in Poisson geometry, which I wrote in the beginning, and let me just repeat it. So that's then for your functions, the observables are now functions of the Poisson manifold. Your functional phi has to satisfy this condition, so that's the beta. And I'm writing it already in the sort of the infinitesimal version. I take also a time derivative of this equation to have here the infinitesimal generator and not the automorphism group directly, so that there's a vector field I will acting on F and multiplying here to X. So X will be some Poisson vector field on your favorite Poisson manifold. That's the Poisson bracket here, of course. And F and G will be functions, and so there will be smooth functions. And because these functionals typically will involve integrations over certain things, yeah, it's good to restrict here to test functions. Yeah, so this will be test functions.
Stefan?
Yeah.
Just one question. So this X of F, it's not necessarily Poisson bracket with some function, or is it?
No, it's a Poisson vector field. It can be Hamiltonian, but doesn't need to. Okay. Yeah. And in fact, interesting things happen if it's not Hamiltonian, but just Poisson. Yeah. I mean, in the symplectic case, there's not much of a difference, but there is a difference. Yeah. In the Poisson world, the difference is enormous. Yeah. I mean, there you typically have an infinite dimensional first Poisson cohomology. Yeah? So there might be a lot of Poisson vector fields of interest also, and which are not Hamiltonian. Yeah? So this is one thing I would explicitly allow for. Yeah. So let's remark this. Yeah. So this is not necessarily Hamiltonian. Can be, but doesn't have to. Yeah. So it's a good question. Yeah. So that's then the semi-classical limit, if you want, of this KMS condition. And I don't know where this really showed up first, but we found papers of Galavotti and collaborators in the mid-70s. Yeah? So they looked for this equation in the context of phase transitions in classical systems, and they had certain infinite dimensional systems in mind. Yeah? And that's where this showed up. At least maybe it showed up before. I don't know. Yeah? And then also for the history, maybe that there's also Flato, Michnirovic and Sternheimer in the 83. They discussed this kind of functional and in the context of deformation theory, both classically and from the point of view of star products of deformation quantization. And then, well, there was maybe a bit dormant the inside Poisson geometry. And then, of course, you all know that Alan's paper in the 97, I think, yeah. So where this was then investigated in the context of the modular class, yeah. And I will come back to that, yeah. So that's where the modular class, that's one motivation where the modular class comes from. Yeah? Okay, so the idea is now we have this kind of condition here. We specify a time evolution, a Poisson vector field on our Poisson manifold. We specify a temperature beta positive, and then we want to understand how many such functionals do we have. Yeah? So the big goal is to understand how many KMS functionals on M with a Poisson structure pi for a given vector field and a given temperature do we have. Yeah? This is the thing we want to understand. Yeah? And I have to argue that this is not completely hopeless and that it contains hopefully interesting information about the geometry, and maybe it's even useful for physics, who knows. Yeah? And maybe I should make one more assumption to make this a bit more approachable. So these are functionals such that phi is positive. So that means it takes positive functions to positive numbers. Yeah? You can take it real or complex linear as you know, this is not important, but this positivity is a very useful assumption. This means it's a distribution of order 0, so it's a measure, it's an integration for a Borel measure such that compact subsets have finite volume. That's the usual Ries representation theorem. Yeah? So we are talking about certain measures on our positive measures on our manifold, which we want to understand. You can of course say, well, if we work here with C infinity with test function, it would be more natural to allow for general distributions, y order 0. Yeah, so would be true. You would get, in some cases, you would get more KMS functionals, not much more actually, but sometimes you would get more, and it's, well, we have not done that for the reason that if you really believe that these things should have the interpretation, the physical interpretation of states, then the positivity is crucial, yeah, for the interpretation. So it's a matter of choice if you want, yeah. Okay, so let's make this assumption here that's a certain regularity, if you want. Yeah? So that's the goal. We want to understand this set here. Yeah, so it satisfies KMS, the KMS condition, of course. Okay, so so let's just make a few comments, a few teasers, and so if you have beta equals 0 or x equals 0, then this simply means phi is a Poisson trace. Yeah? Vanishes on Poisson brackets. Yeah? And vanishing on Poisson brackets, there are, you know, there are maybe not so many functionals doing that, and they are definitely interesting, these functionals. Yeah? So, and typically, this is a pretty complicated set, the set of all Poisson traces, even under the assumption that they are positive functionals. Yeah? So you, even with this assumption, it can be quite complicated. Yeah? And the other remark I want to make is that there's a, because of the way how the x and beta show up, they only show up together. So I can scale beta to 1 by rescaling x or vice versa. Yeah? So there's a certain redundancy here. So we definitely have that the KMS functionals of m pi x and beta, which I assume to be positive, is the same thing as the KMS functionals if I rescale my x to beta x and take beta equal to 1. Yeah, that's trivial. Yeah, but the point is, one typically does not want to do that because the temperature has an intrinsic meaning, the beta, and also the dynamics has an interesting interpretation in your applications. Yeah? If you don't want to rescale your time evolution, I mean, this would mean that everything moves faster. Yeah, but this is a different dynamics then, even though you can of course pass from one to the other in an easy way. So now, I want to give you,
Stefan, just maybe before you continue, one naive and somewhat general question. So does it make sense to consider beta equal to infinity, right? Which would be so to say the zero temperature. Is there a meaningful? Basically, that would probably mean that you throw away the left-hand side, right? On the right-hand side.
Beta equal infinity is a bit more problematic here, right? I mean,
so the left-hand side will be 0 then, right?
Yeah. So this means, I think in the end, I mean, this means that you're looking for ground states.
Yes.
Yeah? So this would be invariant states under the dynamics of x, in particular. That's a necessary condition. Yeah. So you're taking g equal 1 or at least 1 on the support of x, then you see that phi is invariant under x.
But this is only part of the equation. Is a lot more complicated.
It's a lot more complicated because you have the g inside. Yeah? So, but you have to sort of to worry about. I mean, the invariant states, and among them, it should sort of correspond to the ground states. Yeah. So if you have 0 temperature, nothing moves. Yeah. That's sort of the idea physically. We have not looked at that. Yeah?
So one can state the problem, but we don't know what the solution is.
Yes, I think, yeah. I mean, you have to. I mean, it would be. Well, it would be fixed points of x, right? So the pure things would be evaluations at fixed point of the invariant states, but maybe then these are the extreme ones. Yeah,
right. But as you said, this is a somewhat simple condition, but then the equation seems to be a lot more complicated if you have 2 functions, f and g.
Yeah. No, you're right. Yeah,
May I? You formulated quite differently for ground state. Actually, phi x ff conjugate is positive for f. So that's you put together ground state and the ground state and the bottom energy of Hamiltonian is 0. So you put those together into one single statement.
Yeah.
And that's precisely the ground state condition.
Yeah.
So x of x f conjugate is positive for f.
Yeah. So okay. I mean, this. Well, we have not looked at those. Yeah. I mean, I guess that's also there. I guess you have really a very strong dependence also on the dynamics X, of course. Yeah. This is well, I want to tell you some more things here, but this is okay. Let's exclude this case. Yeah, I mean, I'm really talking about positive, maybe beta equals 0. That would be infinite temperature, but beta positive would be my scenario here for the moment. Okay.
Can I ask a question?
Sure.
I think probably one solution, one phi for beta equal to infinity could be just evaluation at the zeros of x, right? And this satisfies the condition that when you evaluate on xf times g, you get 0 automatically.
Yeah, that would be the invariant, and I think that might be the.
So that's the solution. And actually, you can take a linear combination of evaluation on different zeros of x, and this is a.
And then that's that would be the I mean, that would be the extreme ones.
Yes.
Okay. I mean, in general, I mean, because we assume positivity for the phi. Yeah, they form a convex set. Yeah, a convex cone. If I would be able to normalize, it would be a convex and weak star compact set in the operator algebraic context at least, and then the immediate focus would be what are the extreme points of this convex compact subset. Yeah, and then by some Klein-Millmann general nonsense, you know that that the convex subsets sort of can be reconstructed once you know the extreme ones. Yeah, here typically the problem is working with test function. There's of course no immediate sense to normalize things. Yeah, I mean, unless your manifold is compact. Yeah, so it's a convex cone, and then the Klein-Millmann technology is a bit more involved. Yeah, there are some generalizations to convex cones, but we tried to do something in that direction, but this didn't really lead very far. Okay, so where did we stop? Okay, I said this. We have this rescaling here, and now we have sort of. I want to give you sort of three little aspects of the theory. So the first, of course, is the symplectic case. That's what you should do first. The second is the second scenario is regular phi, so meaning that it's the measure is really coming from a smooth smooth integration density, and the third one is the general Poisson case. And well, I don't want to promise too much. Yeah, so here we have some examples and classes of examples, but it's far from the full answer. Yeah? So far away from that. Yeah? And so if you want the take-home message for this talk is here in the general Poisson case, there's still a lot of things to be done, and I guess there's a lot of interesting geometry hidden, and people who know more about Poisson geometry than I do, they should get involved. Yeah, that's maybe the hope here. Yeah, and so okay, let's recap the symplectic case, just as a warming up. And so what can be said here? So the first observation is, and that is what is well known, I guess, is the following. So if you have a functional on the on test functions and m omega is really symplectic here, and let's say connected, with a property that it vanishes on Poisson brackets. So it's a Poisson trace. Yeah, and you don't even need any assumption about your functional. Yeah, so it's a linear functional, full stop. Somewhere in the algebraic dual, not necessarily a distribution. Nevertheless, this is equivalent to that it is a distribution, and in fact, it's the integration with respect to the Liouville measure and some constant. Yeah, so multiple of the Liouville measure. So this is omega wedge omega, and this is some constant. I guess this is a well-known statement, and in some sense it boils down to computation of de Rham cohomology with compact support, right? I mean that's what it's in some sense all about. Yeah. So funny thing I want to emphasize is here no regularity assumption is needed. Yeah. This will change later on, but here in the symplectic case everything is super rigid. Yeah. So there's one trace. Full stop. Yeah? There's up to normalization. There's one trace, yeah? And then little consequence, and that is something I did with Martin Bordemann, Hartmann Römer, myself. I mean that's not very deep, yeah. So if you have here really a symplectic vector field. And you take some beta to positive, and then phi is KMS for this data, if and only if the following holds, and okay, this should be not the zero functional. Yeah, the zero functional is always KMS for all data. Yeah, that's stupid. Yeah, but so it's KMS if and only if X is in fact Hamiltonian, and we have phi is exactly what we did before. It's a multiple of this Gibbs functional. So here it's symplectic Liouville measure, and you integrate with e to the minus beta h, and then it's a multiple of this one here. Yeah. So in particular, in the Poisson cohomology, which in the symplectic case is just a Rham cohomology, yeah, X is trivial. Yeah. So this is necessarily trivial. Yeah. So it's a Hamiltonian time evolution. And you see, I mean, if you want to write down such a functional, you really need the Hamiltonian, right? I mean, this is not a big surprise, and that turns really out to be if and only if. Yeah. So if it's non-zero, of course. Yeah. So that's kind of a trivial consequence. I mean, you plug in this here and verify that it is a KMS state. That's very simple. And to see that if you have a non-Hamiltonian symplectic vector field, then you do that locally, and you see that you can't glue these things together. Yeah? The exponential of e to the minus beta for different choices of h's, they don't glue together. That's in some sense the argument here. Yeah? So in particular, no phase transitions. Yeah, that sort of matches with physics expectation that in finite dimension there should be no phase transitions. Phase transitions is something which only should appear for infinite systems. Yeah? But okay, that's something. Now let's do a few remarks on the Poisson case. Yeah? And the first observation, simply by computation, is that if you look at KMS states on your Poisson manifold for a dynamics X and temperature beta, you have such a KMS functional, then you map it to the following functional phi index H, which I claim to be then a KMS functional for the same dynamics, but now perturbated by a Hamiltonian vector field, that's the H, and same temperature. Let's say here minus sign, I think. And the phi H is just modifying it by this Gibbs factor here. Yeah. So the claim is this thing here is a bijection. Yeah. You can sort of include this factor or not, and the effect of including such an exponential factor of a Hamiltonian function is to change your dynamics by the Hamiltonian vector field. Yeah. This is just compute, plug and play. Yeah. And so what does that mean? Yeah, that means that in fact the KMS functionals, yeah, they sort of only depend up to this trivial bijection. They only depend on the class of your Poisson vector field inside the first Poisson cohomology. Yeah, so this is up to this identification. Yeah, so only the class of X in the first Poisson cohomology matters. Yeah, that's the observation here. Yeah? So you can view that as a kind of a stability under a perturbation of your dynamics by a small dynamics, a Hamiltonian dynamics. Yeah? So this is what people also would expect, that KMS states, they are sort of stable under small perturbations. If you think of equilibrium, if you have a big, if your pot of boiling water is on your stove and you throw in a little bit of more water or less water, it will still boil more or less. Yeah, so it will be stable under small changes, and this is a sort of a precise statement what this should be. Yeah, I mean, such statements of a stability of KMS functionals under small changes of the dynamics, they have been studied in operator algebraic contexts a lot. Yeah, and this is sort of if you want a Poisson version of it. Yeah? So now with this in mind, we can now recall Alan Weinstein's results. So now assume phi of f is really an integration, and this is smooth. So this is a smooth volume form, let's say orientable for simplicity. You can do it with densities in the non-orientable case as well. Yeah? So let's say volume form. Yeah. So then the question is, what happens? What happens here if you look at such a functional for a smooth volume form, and now you define a vector field y depending on the volume form. You take the divergence of the Hamiltonian vector field of f, and this specifies a derivation. Yeah. So this specifies Poisson vector field, in fact, y depending formally on this mu, and then it turns out that for this dynamics, yeah, phi is in fact a KMS state for temperature 1. Yeah? So this is the vector field y mu, and this is the KMS state. Yeah? So starting with a volume form, you can cook up a matching, if you want, a matching dynamics such that this thing is a KMS state. Yeah, this was not exactly Alan Weinstein's argument. He sort of went the other way around. Yeah, looking for functionals for a given dynamics. Yeah, that was our original goal. But here you find something, and you see also from what I said here earlier. Yeah, from this computation here, we see that this Poisson vector field we cook up here is essentially it defines a class in the first Poisson cohomology, which is invariant of the choices of this mu. Yeah? So different mu's, they will differ here by Hamiltonian vector fields. So this class of this guy here in the first Poisson cohomology, and that is of course all what you all know, that's the modular class. Yeah, and that is independent of mu. Yeah? So whatever mu you choose, different choices give you changes, Hamiltonian changes. Yeah? And so that's the regular case in some sense, so the assumption is of course very strong. Why should one have here smooth volume forms? Yeah? In the symplectic case, there was no other choice. Yeah? In the symplectic case, this was all what we had, but here this is really an assumption we have to plug in. Yeah? And now you see, so where do we get? So some consequences is in particular if we have these KMS functionals of m pi and x beta depends only on the class of x in the first Poisson cohomology up to this bijection which I mentioned earlier, and if this thing here is Hamiltonian, so the class is trivial, then this is the Poisson traces. Yeah? And the point is, if I have such a KMS functional for a Hamiltonian vector field, then I can plug in this Gibbs factor with a plus, and then I will get a Poisson trace. Yeah? So Poisson traces sort of control this this set of KMS functionals. Yeah? Okay, so you all know that it's complicated. Yeah, if you don't restrict your Poisson traces to the regular ones, yeah, where you have a smooth integration density, but some kind of measures, then things become much more complicated. Yeah? So now, what a little bit of heuristics before we proceed.
I have a question about that.
Yeah.
Since if you go to the non-regular case, then it looks like it would be also natural to allow the x to be a distribution.
How do you evaluate a distribution on another distribution? This is no. In which sense do you want? I mean, here in your KMS condition, let's scroll here. This is you want this x to be distributional as well?
Yeah. And
plugging it into another distribution?
Well, sometimes you can compose distribution.
Sometimes you can compose, sure, yeah, but maybe you can do that, yeah. Well, I have not thought about that. Yeah, maybe this. I found it complicated enough for ordinary vector fields, to be honest. Yeah, but do you have some particular?
No, I was just thinking that maybe there is some way of defining some distributional modular vector field associated with a distribution, a measure.
I mean, okay. I mean, if you have some scenario in mind, I don't know. Yeah, maybe. Yeah, this could be interesting. Yeah, but well, I mean, at least for me at the moment, the situation seems to be complicated enough to have smooth dynamics x and distributional phi's. Yeah, and I mean, even a distribution in a very mild sense. Yeah, I mean, zero order distributions. Yeah, just measures. Yeah, so it's not that singular. It's more singular than the volume forms here. Yeah, that's true. Yeah, but yeah. So okay, yeah. So if you think of this divergence operator coming from a distribution mu, you would expect some distributional y here. Yeah, that's true. I have no idea. Yeah, if this can be made sense out of. Yeah. Okay. But please interrupt me. Yeah, that's no problem. So okay. But let me maybe just give a little heuristic. So our Poisson manifolds, that's disjoint union of symplectic leaves, right? So these are and therefore you have for a specific leaf, you have this this inclusion here, and you know that this is a Poisson map. Yeah. So in particular, if you pull back Poisson brackets or functions on M, you get the corresponding symplectic Poisson brackets on L. So the idea is, of course, well, define a functional just by taking the pullback of this function f to the leaf, and therefore integrate it with the symplectic volume you have. That would be a Poisson trace on the symplectic leaf. Well, not really. Yeah, and what's the problem? Yeah? The problem is that in most cases, yeah, or well, in the interesting cases, the symplectic leaves, they are not properly embedded. Yeah, so the problem is that the inverse image of some compact subset in L is not necessarily compact. Yeah? So unless, I mean, this is exactly the case when this map, this inclusion here is a proper map. Yeah? But there are, of course, zillions of interesting scenarios where you have leaves which are not proper. Yeah? And so so this function is simply not defined at all. Yeah? And if it would be a trace for free. Yeah? Then things would be very easy, and we would get a sort of good understanding of what the Poisson traces of a Poisson manifold would be. Yeah? And this would sort of be the extremal ones, yeah, in a good sense. Yeah? And the general Poisson traces would be linear combinations of those. But this, unfortunately, doesn't work. Yeah? Unless you have very specific leaves. Yeah? And now there's a question which I would really like to ask here in this audience. Yeah? Of course, to have a proper map iota would be sufficient to make this integral well defined, but something slightly less would be still sufficient. Yeah. To be defined is what I call a small leaf. Sorry. Yeah? And that should simply mean that the integral over the inverse image of a compact subset, which might be non-compact, yeah, of omega L, is nevertheless finite. Yeah? So that they have the inverse images of compacts have at least finite volume, because we have the symplectic form. We do have a volume here, a notion of volume on the leaf. Yeah. So you have your compact subset in M, yeah? And then your leaf is spinning around here. That's maybe bad. Let's take a different color. Yeah? So your leaf is sort of coming back and forth all the time. So the intersection of the leaf and the compact is not compact in L, but it still could have finite volume. Yeah, and I don't know whether this may happen. So I was not able to construct examples. Yeah? Typically, when you go sort of to the boundary of L, the symplectic form sort of has to blow up. It cannot have a smooth extension to beyond, and at least in my understanding, it blows up badly enough so that these volumes are necessarily infinite if you don't have a proper leaf. Yeah, but okay, maybe someone has an idea here. Yeah, would be nice to have an answer if this condition implies that the leaf is proper. Yeah? So this applies. I mean, for general submanifolds or immersed submanifolds equipped with some volume form, this might have there might be small ones, yeah. But in this symplectic situation, this might be more tricky. Okay, so now the last thing I promised you. It's more a question mark. So what we did was to look at the Poisson case, and to give you just a very rough idea what we looked at. So let's take connected Poisson manifold. So that what is that? Yeah, let's recall that. That simply means that the top wedge, so this is 2n dimensional, so the top wedge is transverse to the zero section, the top wedge of the Poisson structure. Yeah. So and that means that we have this singular locus of the Poisson structure, that are those points here where this thing here is actually zero. Yeah? And since this is transverse, this is a nice closed submanifold. I mean, there are a lot of people doing Poisson. I mean, I'm who know this all much better than I do. Yeah, you have to ask Eva, and she can tell you everything about that. Yeah? And so let's assume, yeah, that this is also connected. And it could have many connected components, but let's assume to have this thing connected. Then we do the following. We choose again a volume form, and then we can define function zeta by pairing this volume form with a top power of our pi, and this is now a defining function which turns out to be such that the singular locus is just the inverse image of 0, and 0 is a regular value of this function zeta. Yeah. So so that's the scenario here, and now one can decompose in under these connectedness assumptions. These are, well, you can do it also with more than one connected component, but then the combinatorics becomes a bit more tricky. Yeah. So under this assumption, you have that your M decomposes into the zero locus, into the place where zeta is positive, and into the place where zeta is negative. Sorry, and these are all connected. Yeah. So now let's see how do Poisson vector fields look like. Yeah. So let's one does the following. You need these B forms, this boundary geometry 1 forms. So you take a theta to be a 1 form on M, but in this B form there should be a B here, and for your Poisson vector field, and then you find such a theta, so that the sharp of this guy is exactly the x. Yeah, so they differ only by a Hamiltonian vector field. Such a boundary 1 form exists. Yeah, that's the and so it's boundary closed. Yeah, so this is a B closed. Yeah, a B closed 1 form, and in fact you can look at thetas where you have some parameter. So this is a constant, and then this is this singular part of the B, and then there will be some this will be a regular or a smooth 1 form here on M closed. one form here, and from those you can cook up all classes of Poisson vector fields here. Yeah, and if you just take this d zeta over zeta, that I think is the that's maybe up to a sign. That's why I included the minus sign here. That's the modular vector field. Now the question is, or what we determined is how the I should make it more up here. Let's do that. I have all things here. So what is now the KMS functionals in this situation? So for the class of this theta and our inverse temperature. Yeah? So that's what we want to know. And there's there are certain cases, yeah, depending on the, well, if we fix beta to be positive, yeah, so this is always the convention, then the relative sign of A and beta matters, yeah, so it really matters whether A is positive or negative, this relative to beta, yeah, and since for beta we fix the sign, then we will get the following table. So we have the case where A is positive, A is 0, so we have sort of no singular contribution here, but only coming from regular one forms, and A negative. Yeah? And then the other interesting information is what does the one form theta here, the regular little theta, do? Yeah? And so there are different cases. So if we restrict theta to the big open chunk beside the singular locus and take its de Rham cohomology class and assume that this one is 0, so this is Hamiltonian, that's a Hamiltonian condition, then we can write down things here as follows. So we have sort of two parameters for free, two positive parameters for free in the number of KMS states for A bigger than 0. We have, for A being 0, we have all KMS states on the induced Poisson structure on the critical locus. And here we only have the 0 functional. Yeah. So everything here in this situation, everything sort of happens on the critical locus. And if the class theta is non-trivial, then we don't have anything here. That's sort of corresponds to this earlier symplectic situation. Here we again get things which only happen on the singular locus, and now the vector field is really the little theta sharp on the singular locus and beta. And these are the Poisson traces. Here we really have KMS states, and here we again have nothing. And so let me just, I forgot the formula. Where is this? No. Yes, and maybe I should explain this thing here. How do these two parameters show up? Yeah? So the functionals we have here is how do the KMS functionals look like? This means that beside the critical locus, we have Hamiltonians, yeah? And so we have a Hamiltonian on the plus part, and we have a Hamiltonian on the minus part for the little theta. Yeah? And so this is sort of a linear combination for the plus and minus part of the integration over the plus and minus part for the Liouville measure, or this volume we've chosen before. We integrate the function, we have the usual Gibbs factor, and then sort of as a correction to make this the symplectic volume, we have here this combination -1. Yeah? So the A is this A here. Yeah? Beta is our inverse temperature, and then there's this factor of the theta which sort of goes to 0 when we move to the singular locus, and you see it depends a bit on how singular these things become. And these two parameters here, these are the two constants which we have here. Yeah. So okay, well, you will immediately forget about this table. Yeah, this is maybe not even very interesting, and it caused us some pain to prove it. But the important message I would like to give you here is that there are general statements possible. Yeah, so this part, of course, stays a bit unclear because it refers now to KMS states or Poisson traces on the induced Poisson structure on the zero locus. Yeah, so many things can happen. Essentially, everything can happen. But here, these parts here, they I think are pretty interesting. That one can actually determine them and say something. Yeah, and so I guess the conclusion and well, we had also some other very isolated examples. Yeah? This is a class of examples, if you want. But the conclusion is the following. So I guess it is interesting. We had this, didn't have time now to discuss. We have examples that very ad hoc examples, very explicit examples that KMS tells something about how singular leaves, or how singular the leaves sit inside M. Yeah, so it really matters whether it's a proper inclusion or not, and the or not can be quantified by means of KMS functionals. That was in one of these examples I didn't tell you, and well, we need more examples to get a clearer picture. And then, of course, the ultimate goal, at least for me, would be to pass to quantization. That this is and for me, quantization would be deformation quantization. So we want to do this quantum KMS states. Yeah, the classical limits would be something like that. And now the question is, can we deform KMS functionals for a given star product here, and in the symplectic case, yes, we can do that because we can deform traces. This is something one knows, that the traces, there's one trace up to normalization in the symplectic case, so Richard knows everything about that. So using this result, it's easy to write down the deformation of the KMS function in the symplectic case. But in the Poisson case, this I think is very interesting. Traces have been considered in the context of cyclic formality theorems, but the KMS functionals do not necessarily come from traces, and then things are, I guess, pretty much open. And yeah, so let me stop here, and I'm sorry I'm over time already, I guess. Yeah, but yeah. Let's stop here. Thank you.
Thank you, Stefan. Please, questions or comments?
May I, please? Yeah. Stefan?
Yeah.
About the last case the example you gave about the B symplectic manifolds.
Yeah.
That integral you wrote down on the one page back.
Yeah, this one here.
Yeah, is that an integral with a pole? Is it the principal value of an integral?
No, that is done in a way that it converges. Yeah, it is over the part where this function zeta is either positive or negative, yeah? and this should be possible without difficulty, because well, the zeta and the mu, yeah, they talk to each other, yeah. We fixed one volume form. Let's go back here. We fixed the volume form, and then we computed the corresponding zeta, which produced the singular locus. Yeah. And I mean, there are many functions producing the singular locus, but this is a choice. Yeah. And this depends on the mu, and we take the same mu here. Yeah? This is the same mu, and that sort of makes this combination nice enough so that these integrals here converge. Yeah.
Okay.
Yeah. I mean, it's not obvious. Yeah. It's one has to take a closer look. Yeah.
Another question about the same example, if I may.
Sure.
That Poisson tensor restricted to the hypersurface. That's of constant rank, is it not? I think it's called rank 1, maybe.
Oh, this is a good question. I should ask the Poisson people. Is that
I believe the symplectic leaves of codimension 1 inside the hypersurface.
Yeah, maybe, yeah. Mm-hmm. Yeah.
So that leads to the question: if your Poisson tensor has constant rank, can you say anything more particular about the space of KMS functionals?
Well, I can't. I didn't look at it, but I guess this would be maybe a feasible class of examples. Yeah. This would be, well, maybe one of the next ones. Yeah. I mean, this constant rank that sort of brings you a little bit in the symplectic scenario. Yeah. That you're. I mean, the trick is always in this one here. Yeah. To exploit this kind of big chunks where you have the unique symplectic situation. Yeah. And if you have random leaves, yeah, with arbitrary dimension, then this doesn't really help, because the leaves sort of are sitting inside M in a too nasty way. Yeah? But here, this symplectic situation, it's symplectic enough to make this kind of uniqueness statements. But maybe the constant rank, yeah, would be, I guess, a very interesting class to take a look at.
Also, in the B symplectic case, the hypersurface very often fibers. And the leaves are the fibers of a fibration, so they're closed leaves. So you have a good case where you have these proper embedded.
Then
leaves.
you have the properness, right? Then you should be able to say something. That's true. Yeah.
Okay.
Yeah.
Okay. Thank you. Yeah. Thank you very much.
Yeah. I mean, if you have a proper, I mean, this means that the image is closed, right? I mean, then this is what you need. Then you can say something. Yeah. Then you have much better control.
Okay. More questions or comments?
And I have a comment. In this particular case, the modular class would be 0. We know it's 0 on Z. So does this imply something directly if you know that the modular class is 0?
Then you have to, if the modular class is 0, then the KMS functionals are for the Hamiltonian dynamics, they are determined by the Poisson traces. So you're back at the Poisson traces. Exactly. And then, well, I guess you still can have a lot of complicated space of Poisson traces. Yeah. But of course, then you know what you look for. Yeah, I mean the Poisson traces. This is complicated enough, but that's it. Yeah. So the KMS in this case reduces to KMS of Hamiltonian guys, I think, and then you should look for the Poisson traces.
More questions?
Yeah, maybe. Yeah.
Hi, Stefan.
Hello.
Wanted to ask you, do you know of a version of the KMS condition, but at the level of a symplectic groupoid? because my feeling is that that would be the true semi-classical limit of the quantum version. I don't know if Alan mentioned this in one of the papers or. So I am thinking that there might be some measure on the groupoid, and there will be some compatibility with multiplication and some, and the equation that you have would be a limit of that, or you know, consequence.
I have no idea, yeah, but maybe yes, this would be yet another turn of the story, and would bring, of course, a whole new machinery into the game. Yeah, this would be great. Yeah? But I don't know. Sorry, I only raise questions and have no answers. I feel.
Okay, thank you.
Yeah, but that would be nice to encode this on the level one upstairs, right, on the level of the symplectic groupoid. Yeah.
Okay, further questions, with or without answers?
So sorry.
Yeah, further question. I'm just asking for further questions.
Yeah.
Yeah, there is a question. There is a hand up by Pedro.
Yep. Pedro, go ahead.
Yeah.
Oh, we can't hear you.
Yeah, you need to unmute yourself. So
I feel he is unmuted and it's still not working. No.
Yeah, we can't hear you, Pedro. No.
But you can type your question in the chat and we're going to read it.
Maybe like that, yeah. So sorry. Yeah.
Because your mic probably doesn't work or something.
So where do we see this? I can also stop this sharing here. But...
Yeah, he's typing the question in the chat.
Can I ask a gratuitous question in the meantime?
Sure.
Go ahead.
Yes, thank you. Well, what about linear Poisson structures?
Yeah, that's also one thing on the agenda. Yeah. Again, I mean, Poisson traces, morally, they correspond to coadjoint orbits by what I say here, right? And but not in all Lie algebras coadjoint orbits are really embedded submanifolds, right? I mean, this is the compact case. Yeah. So in the compact case, I guess one should be able to say a lot more. Yeah. And if you have then, on the other hand, in the non-compact case, if you have these more funny orbits, yeah, then the game, I guess, is pretty much open. But there again, yeah, this is one of the scenarios we want to take a look at. The linear cases should be very, at least one should be able to say something. Yeah.
So Stefan, now you can read the question of Pedro. I can read it. So he's asking about the infinite dimensional case. And so I guess one imagines some kind of field theory, classical field theory system. And it kind of is all right. So he's also given some reference to a preprint of Amari and Soniger, where they show that Gibbs measures are the only KMS states for a family of nonlinear Hamiltonian PDEs. Well,
okay. Yeah, I mean, that's where the whole story comes from, right? I mean, it comes from infinite dimensional systems as a replacement for the Gibbs functionals, as I said in the beginning, yeah, because that usually is very hard to make sense out of in quantum field theories. And of course, one can ask the question about these classical KMS states in classical field theories, and I have no clue about that. Yeah? And what one can do, and this I've not seen much of that. I think that if I remember correctly, a student of Klaus Fredenhagen did something. Pedro, you probably know him in Hamburg, but that's quite some time ago. But I think there's I mean, people studied a lot, yeah, the situation of KMS states for this in axiomatic quantum field theory, these Haag-Kastler scenarios. There are people really there are zillions of books about that, textbooks, classical textbooks, where they study this. Yeah, but I think it's really always a quantum scenario. Yeah. On the other hand, thinking of this robustness of the KMS states, you would sort of expect that whether classical or quantum, I mean, from a physical point of view, this should not really make a big difference. Yeah, everything is boiled, right? So this is thermodynamical equilibrium states should be sort of semi-classical anyway. Yeah, but infinite dimensional systems, I can't say much, Pedro. Yeah, this is another.
So now, people, you can see the continuation of Pedro's question, including the archive reference. So, I mean, for those who are interested, you can click on it. So, other questions or comments? Maybe I have a question again about your B Poisson example. So there we have a family of these two parameters, right?
Yeah.
So according to what you said in the beginning, we should think that this would correspond to some phase transition, right?
Yeah, I mean, in some sense, it corresponds to the two pieces left and right of the zero locus. Yeah.
Wait, it's not my question yet, right?
Okay.
Right. So my question is, can you imagine some scenario in this case of quantization, maybe some very simple B Poisson structure, right? But I mean, where you would see some quantum phase transition, because in the beginning you told us that like those finite dimensional situations, they're probably there. You don't expect phase transitions, yet you now show us just a whole family of examples where you seem to have, according to your definition, some classical phase transitions. Can one hook up some quantum example, maybe some very, very particularly simple case? What would correspond to?
I think so, and we should ask Richard. He has some very old paper from the late 90s, early 2000s on this. You called it symplectic Lie algebroids, I think, right? This paper, and so it's so. Do you have the traces there as well? For the star products you construct, is this?
Well, you have traces and you have higher cyclical cycles. So, for example, for this B boundary case, so B case,
yeah,
you have a higher cyclical cycles. There's no trace, but there's a one cocycle.
Yeah. So
that's connected with this modular class, of course.
Yeah. So maybe this is the first place to take a look. Yeah.
No, but this the fact that these are phase transitions, it's fairly standard in physics, in quantum statistical physics. So the first example you can write down is, say, spin chains.
Yeah.
When you compute phase transition, you actually find out when you have a change in KMS state.
Yeah. And I mean, the slogan I learned in physics was that in finite systems this doesn't happen. Yeah, but I think the spin chains, it's really the chain, the infinite chain. Yeah,
infinite. Yeah, of course, yes.
So yes. This is, it's not just a ring. But okay, this is a physics slogan, and it in some sense refers to a symplectic situation, I guess. Yeah, the Poisson situation is maybe simply not covered. Yeah, by
sure. Poisson situation is much more complicated. Yes.
Yeah, and so there, one should not sort of overdo this physics slogan that there are no phase transitions. Yeah,
no, but there are phase transitions.
Yeah. That's
phase transitions.
No. I mean, in finite dimensional.
No, in finite. No, because sorry, but because in finite dimensional. Okay, in finite dimensional case, this KMS state is just a Gibbs state.
Yeah.
It's the same as a Gibbs state with respect to some Hamiltonian. It's literally the same.
Yeah, yeah.
So and different Hamiltonians give different states. So this there is problem is that you don't have this. Okay, differently. If you think about the measure theoretic situation, not smooth and continuous, not C-star algebra, but let's say von Neumann algebra.
Yeah.
So measure theoretic situation. Then KMS, then you have, well, it's not type 1 general, so you don't have a trace that has some weight, and the KMS has unique KMS structure.
Yeah, yeah.
So the one parameter group of automorphism is unique up to inner perturbation.
That's this
Tomita-Takasaki. Right. So in measure theoretic sense, there's unique situation. Right. Yeah. And then the question is, if you start with a say smooth structure, and then you can embed different embeddings into a measure theoretic situation, give you different examples. Right. And this phase transition is corresponds to different embeddings into measure theoretic structure, but it's like change of spin from O spins up to O spins down, for example. Right, so the composition, you have these two states, so this spin chain, right? So you have the phase transition is as long as temperature is high enough, there is a unique KMS state which corresponds to Gibbs state. Right? The moment the temperature drops below critical temperature, suddenly you have two KMS states, the same temperature.
Yeah.
O spins up, O spins down.
Yeah.
Right? And it's physical, but it has to be in 10-dimensional system.
Yeah. Yeah.
Because everything is modular of these Gibbs type perturbations.
Yeah. Yeah. And they yeah.
Okay. Thank you. In the meantime, there is a discussion on the chat between Francis and Nicolò. I don't know whether Stefan would like to look at it and maybe react in some way.
Then I think I have to stop sharing, right? I know. Can I view the chat here?
Oh, I don't know. Maybe.
No, I can view it. Sorry, I can do that. Yeah. let me see.
So that's about the homology interpretation of KMS state. And then Nicolò is suggesting that this is maybe some twisting of the.
Yeah, I mean it is. I mean the 0-1, the traces are 0 Poisson homology. Yeah, that's but for the KMS, it is a sort of perturbation of that. I don't know. Yeah, maybe one can. I mean, it would match sort of this robustness statement, right? I mean, this but yeah.
All right. So more questions or comments? Well, if not, or was there someone? So if there are no more questions or comments, let's thank Stefan again.
Thank you very much.
Ed Voronov will be speaking on global Poisson. Thanks a lot, everybody, and see you next week.
Okay. See you. Bye.
Bye, everyone.
Bye, Stefan.
Bye.
Bye, Richard.
Richard, yeah.
Hi, Stefan.
It was nice to see you all here. Yeah, that was good. Very good.
Ciao.
Okay. Ciao.
Bye.